Welcome to the 17th lecture from chapter number 8. We are studying VLSI design, and today we will study branching effort. It is a small recap of what we have been studying for the last few lectures. Logical effort is defined for well-defined paths, and we have studied G, small g, logical effort of a gate, capital G, logical effort of path. We have studied small h, electrical effort of a gate, capital H, electrical effort of the path, and the path effort, capital F, which is the product of G and H. This is what we have been studying. And delay, which is equal to n times f to the 1 over n plus parasitic delays. And we have studied techniques to minimize these delays by adding extra inverters in the chain whose addition doesn't affect this capital F, the path chain. This is what we have been studying for the past few lectures. Today we will study branching effort. Branching effort comes into play when we have a chain where the output of one gate is being used to feed two or more than two gates. In this given chain, we have two such points. This point where the output of this NAND gate is called, let's give them some numbers, 1, 2, 3, 4, 5 and 6. Output of gate number 2 is being used to drive gate number 3 and gate number 4. And we have a branching here at this point, let's call it B2 point or B2 node, where the output of gate number 4 is driving gate number 5 and gate number 6. So this branching also introduces an effect which we call as branching effort, and we represent it with small b, where small b is the ratio between two capacitances, where CT is the total capacitance and C path is the input capacitance of the gate for which is in the path. Before we use branching effort, we have to define the path we are considering. Here, this is the input, and with this blue dotted line, I have mentioned the path for which I am going to compute this effort. So at the output of this gate number 2 at node B1, we have a capacitance, we call it C path, that is the capacitance of the gate, in fact input capacitance of the gate in the path. Here we have at the output of this gate number 2, this gate number 4 is in the path, so its input capacitance is C path, the capacitance of the gate that is in the path, whereas CT is the quantity in the numerator is C path plus C off, the capacitance of the gate that is in the path plus capacitance of the gate or gates that are off path. This gate 3 is off path, so C off is capacitance, input capacitance of the gate off the path, that is off the path. So once we have understood that, the total branching effort, capital B, but that is the branching effort of the path, is defined as, for all nodes where we have branching effort, valid branching effort times not GI, this is BI, the product of all individual branching effort numbers, all individual branching efforts. So in this given chain, we have 2 points where we should calculate branching effort. This point B1 and B2. For B1, CT, the total capacitance, is the input capacitance of the gate that is in the path plus the input capacitance of the gate that is off the path. The input capacitance of NAND 2 plus the input capacitance of NOR 2 divided by the input capacitance of the gate that is in the path, that is gate number 4, NAND 2. We know that for NAND 2, the input capacitance we have computed in previous lectures, this is R plus 2. For NOR 2, this is 2R plus 1. For NAND 2, this is R plus 2. So this is the branching effort for node 1, B1. For node 2, or for the second branch, we can compute branching effort in the same way. For B2, we have this NOR gate, gate number 6 in the path, and this NOT off path. So their sum of their input capacitance should be in the numerator. So the input capacitance of this 2 input NOR is 2R plus 1. The input capacitance of the standard NOT gate we already know is R plus 1 divided by the input capacitance of the path in the gate in the path, that is the NOR gate, gate number 6, 2R plus 1. So this is how we can compute B2. And finally, and another thing that we should observe is that in the numerator we have this plus sign. In the numerator, the term in the numerator is larger than the term in the denominator. So for any branch Bi, the value is always greater than 1, because the quantity in the numerator is always greater than the quantity in the denominator. So therefore the answer is greater than 1. And the total branching effort, we call it branching effort of the path, can be computed as 1 to 2 Bi, B1 times B2. So we can plug these values in here. This left the homework for student, and find the branching effort of the path. And you can test it for any given value of R, maybe for 2.5, and check whether this branching effort gives you a valid number that is greater than 1. Total path effort, we have studied about the total path effort F to be the product of G and H, where G is the total path effort, total logical effort, the path logical effort, where H is the path electrical effort. We can now where we have the effect of branching, this F, the new value of F would be, or new expression for F would be G times H times B, where B is the path branching effort. So the new F would be this if there is some branching effect in the chain. We'll continue studying about gate delays in our upcoming lectures. Thank you.